Welcome back to the second lecture of today, the third lecture overall. So, as you might have noticed in the original title of the lecture series, there was this word constructible appearing, but so far I haven't told you yet what that means. So the third lecture is going to be about locally constant / constructible factorization algebras. And so let's recall an example that I gave very beginning that, for example, we had this sort of algebra that looked like this, where we had some associative algebras, and then some modules. And then I claimed that there is an algebra on R, but where somehow 2 points of R had a special role because the value here was n, value here was n, and then the value of these other opens was A, B, and C respectively. And so you see that on this factorization algebra, only a very small number of different values appear. Then we also computed the value of the whole thing. And this is a very common phenomenon. And in fact, one can even start with a very basic version of this, where you don't even have any of these special points. So let me just start by giving you a definition, which is in the case where X is a manifold. And I guess for this definition, it doesn't really matter if you take smooth or topological, you will get respectively a definition. We will mostly be working with smooth things, but that's not really that relevant for this lecture series. So you can make the following definition: a factorization algebra on X. So let's say A is called locally constant if so whenever you have an inclusion of U into V, this in the opens X, such that both U and V are abstractly isomorphic to this, so that means that both U and V are isomorphic to Rn. So let's say this is an n manifold. So this I will just say that U and V are both embedded disks. Then we want that our algebra, the value, the map from A of U to A of V is an equivalence. So the idea is that somehow, by some of the things I explained earlier, the value of a factorization algebra is essentially determined by what it does in disks. And this tells you that when you move from one disk to a slightly bigger disk, the value of your algebra doesn't change. And of course, an example is the one we had very early in the course, where you really just have an associative algebra, and then you have a factorization algebra on R, which to each disk just assigns A. And of course, to disjoint unions of disks, it assigns A tensor A, but like to each disk, it assigns A. And then, of course, if you have one disk in a bigger disk, here you have just the identity, or maybe an equivalence if this is any one algebra. But you see that this definition will not be able to capture situations such as this, where we have some special disks inside R, which are the ones which contain one of these marked points here, where we will allow there to be the value here will be different from, for instance, so the value, this disk sits inside, okay, I should probably use a color. So this purple disk sits inside this bigger purple disk, and the value here is B, and the value of this bigger disk is M, because it contains this point. And so, of course, we don't want, this would be an example that's not locally constant in this sense. And so what we would like to have is a more general definition, and that's where this constructibility comes in. Okay, so to deal with many examples, introduce constructibility. And this is something that takes place on stratified spaces. And so I will give a very, very short crash course on the type of stratified spaces we will be talking. So this will be very brief crash course. Okay, so first of all, a stratified space is a topological space X plus surjection from X onto some coset, where this carries the coset topology. Continuous surjection. And just to give you an example, so let's say we have a S1, and I could say I endow this with a stratification where I mark these 3 points, and let's say I have a map to the coset that looks like this. I have A, B, C, and then I have X, Y, Z, and then the arrows like this that indicate the coset structure. And if I send these points to A, B, C respectively, and everything that's in these areas here to Y, B, A, X, and Z, then this would be one possible stratification of S1. But of course, often we want the stratification to be somehow more uniform in the dimensions. So the same picture, I could also just draw it, I guess, it looks like this. By just saying this goes to 0, this goes to 0, this goes to 0, this goes to 1, this goes to 1, this goes to 1, where this goes to the thing that's now just a coset 0 smaller than 1. So these are example stratified spaces, and there's one key construction we will need about stratified spaces. No space here, so I'll just use a different board. But this isn't working, so
don't worry.
Thank you. So there's the following construction. Which says that if we have a stratified space, then we can build a new stratified space, which is the so-called the cone on X. This is just the usual cone from algebraic topology. It's like the open version of this cone. So it's like you take the interval from 0 to 1 as a half open interval times X, and you collapse the initial part. So this will be pictorially, you will have like X, and then the cone will look like this. And the way you stratify this is you say that the cone point, so this will be stratified over the coset where you have the same coset as P, but you add one more minimal element. So this is a join, so this is a smaller than every element in P. And there will be a stratification of this, which sends this new cone point to the minimal element minus infinity, and every other element, so the ones that live in this part, here you just use the old stratification by first projecting onto X and then using the old stratification. So as an example, if we take the cone of the picture I just drew, then it will look like this. So since it's an open cone, I will have and open this, I will have a new cone point in the middle. So instead of drawing it like this, I will flatten it and look at it from the top. And then these 3 points that were a single stratum before, I'm taking them across an interval, so it now looks like this. So I have now 3 types of strata. I have minus infinity. This is the thing that was 0 before. And then I have this whole thing here, which is the stratum number 1, which goes to minus infinity 0. Of course, then in practice, one will probably relabel this so that this becomes 0, 1, 2, just to match the dimension. But yeah, this is what it is. So these are the cones, and these cones, they will play the role of the disks in our theory. So these are now more general disks that have a much more complicated inner structure, but they will be the thing that we will care about when talking about constructibility. And so now we can define stratified manifolds. So this is the following definition, which was introduced by L. Francis Tanaka in this form. So a stratified manifold or I guess this is also what they call a C0 stratified space, is a space, and there's some points in topology adjectives here that are not really relevant, like second countable, paracompact, maybe Hausdorff. Maybe some of these imply the others, I'm not sure. But anyway, we can forget about this. The relevant part being such that. So there's supposed to be some sort of manifolds, like so no smooth, not smooth, but like topological manifolds. So what does that mean? So that means they need to admit a cover, an open cover. And like for an ordinary topological manifold, you would just say they admit an open cover by disks. But now, sorry, I should have said the stratified space. And they admit an open cover no longer by ordinary disks, but by conical disks. And I haven't told you what that means yet. So this definition, we're defining 2 things by mutually recursing over each other. So I'm going to have to tell you what a conical disk is. And that will be defined in terms of stratified manifolds. So a conical disk is a stratified manifold that is isomorphic as stratified manifold, but like abstracted, to one of the following form, to one of the form which I would call d x comma n. And what is this? So this is, I take the cone on x across some Rn, where x here is any compact stratified manifold. And this thing, the way it is stratified, so here the stratification, it goes by this Rn component has trivial stratification. So the way I stratify this is I just project onto the cone component and then use the stratification of the cone, where here x was over p. So these 2 are defined inductively via each other. So this might be a little bit confusing to parse. So let me draw some pictures to show you how this looks like. No, not yet. This is like what you would think of as a topological manifold. So there's no assumption or transition map yet. I will then write the version where you have some smoothness on the transition function. So this you should think of as the stratified analog of a topological manifold, as opposed to smooth.
What's the definition? So with the point.
No, this follows. I will show you. So let's start. So the empty set has a cover by conical disks. I mean, the empty set. The empty cover of this consists of conical disks, whatever they are. It's an empty set. So this is a stratified manifold. Then you can take the cone on it, and then even times some Rn. And so this will just be Rn. So this in particular will be a stratified manifold. So and therefore in particular everything that can be covered by these. So all ordinary manifolds are examples of stratified manifolds. But then you can also do something like this, where you say, okay, S0, this is a manifold, so in particular a stratified manifold. And then you can take the cone on it, for example. And then this looks like this. Which is, this is a picture we already saw. This is R, but stratified, where I have a stratum with 0. And then this picture I already drew. So this S1, it can now be locally covered by things that are either of this shape. So around each of these points, I have a cover of this form. And around the other places, I have just an ordinary interval. So this one is a stratified manifold. And then I end by passing cones. We will see that this thing I drew here is in fact a stratified disk. That's a conical disk. Okay. Just to give you one more example, which is something that doesn't happen for ordinary manifolds, but does happen for stratified manifolds, which is you can take S0, disjunct S1. This is a perfectly valid manifold. This is even an ordinary manifold. It doesn't have a constant dimension, but okay. So this is a manifold that is, of course, compact. And so you can take its cone. And if you draw what this is, you see that the S1 coordinate gives you like a thing that looks like this, and then the S0 coordinate gives you two more rays like that. So if you write what this is really R2. This is a copy of R2, stratified at 0, and then glued together along this point to two copies of R bigger or equal than 0. And so you see that this is a stratified manifold, but it doesn't have a well-defined dimension because it has pieces that are of dimension 1 and pieces that are of dimension 2. So even connected stratified manifolds need not have a well-defined global dimension. Okay. So, but also note that since all the cones, so by definition, to be a stratified, or to be a conical stratified disk, it has to be a cone on a compact stratified manifold. This compactness is rather important because it means that the dimension of this thing on which you take the cone over will at least be bounded. And so that means at the very least, stratified manifolds have locally finite dimension. Even though they might not have globally finite dimension. Okay, so this is like a little crash course on these topological manifolds that appear. And the thing that we're actually going to be using for the talk are the smooth version of this. So this comes back to the question that somebody in the audience asked before. And I'm going to be extremely sketchy about this. I'm just going to basically tell you that one can do this. So this is again AFT. They recursively also define smooth conical manifolds. Which I guess they call also conically smooth stratified spaces. So these are so they have an atlas by smooth conical disks such that the transition functions are conically smooth. And I will not go into details of how one defines these terms. I will state a bunch of important facts about this, and we're just going to be working with those. So basically, so all these three terms, they're somehow defined recursively via each other, where a smooth conical disk, in the same way as we did before, is just a cone on a smooth conical manifold that is compact and that you already have. And then between such smooth conical disks, you can define the notion of conical smoothness with respect to the notion of smoothness here. And then the smooth maps here, we do them like we would ordinarily do with smooth manifolds, where you have to have a map that's smooth on each of the pieces of the atlas. So yeah, this is a kind of complicated recursive definition, which I will omit the details here because they're very hard to understand when reading them at first, and they're not that relevant for this talk. Okay, so there's one key fact. We will need a few more facts later, but the one main fact that these smooth conical manifolds satisfy is that when X is a smooth conical manifold, then if you look at these pictures, what you will observe is that whenever you pick a point anywhere, it will sit on some stratum. And then if you zoom in far enough on that point, the type of disk that exists around that point, at some point there will be only one type of disk left. So that's the following statement. So whenever you have any point in X, then there exists a unique Z and N, of course Z up to ISO, and N a natural number, such that if you look at the opens, if you look at the opens around that point, which are abstractly isomorphic to the standard disk of type Z, N, so that's where the Z, this is a compact manifold of a lower dimension, this is some number, and if you look at only those opens that have that type, so here we say that U is a disk of type B, Z, N. And if you only look at those disks, then this should form a neighborhood basis of around X. So there's going to be one specific type, which we then call the local type at X. And if you look at the pictures, you will see, let me do an example. Actually, yeah, but I think I had another picture I wanted to draw. I guess not here. Okay, I will just use this picture. So if you look at any point around here, then its local type will just be a usual unstratified disk. But like, for example, if you look at a disk, if you look at this point, the local type around it will be a disk that somehow, yeah, okay. I mean, I guess this whole thing, that's what it is. So Yeah, okay. Maybe this is not the best example. Okay. But now, using this, we can finally define the notion of constructibility, which is the thing we wanted to do for a while. And we just mimic the same definition as for local inconstancy, except that we need to take into account these different types of disks that can now appear. So let's see, which one should I erase? Probably. Definition. And say that X is a smooth manifold. And then we say that a factorization algebra on X is called constructible if, again, it induces an equivalence from AU to AV whenever U into V are conical disks of the same type. So that means they're both abstractly isomorphic to the same standard disk like this, but of course this inclusion needs not to have anything to do with these abstract isomorphisms. And now we see that with this definition, the examples we saw before, they do in fact have the property. So example, so that we have, for example, a bimodule, AB, then here we see that there are two types of disks. There are the types that look like this. Those get sent to M. Then there are these two, a priori, so they have the same type. So you might think, oh, maybe they should be sent to the same thing. But actually, you see there's no inclusion of one of these into one of these because they live on different sides. So this condition is not going to allow us to compare the value here with the value here. And then, for example, we will have the inclusion of this disk into this disk. And while this is an inclusion of this, so if it was a locally constant factorization algebra, it would have to be equivalent. For the constructible ones, it doesn't, because these are disks of different types. One of them is a disk of type R, and the other one is a disk of type common as 0.
With yellow and the filter.
Yes, thank you. That's a good idea. This one can probably not see as much. Okay. So like this type here, this is R, which is not isomorphic to the cone of S0, which is this type. They're both disks, but they're not isomorphic as stratified manifolds. Okay. And now using this, we can define a category. So we define, so we define manifolds. So this n is a straight n. Later we will get curly n, and again I will try to be a bit careful with the topography. So this is the one category of smooth stratified manifolds and open embeddings. So I mean, of course, maybe I should decorate it with the stratified, but like by default, all manifolds will be stratified, so I will just use this notation. And then inside it, we have the full subcategory on the stratified disks, on the conical disks. And then similarly to before, if I add an S here, it's like the multi-disks. So disjoint union of disks. And finally, note that if you take manifolds and you slice them over a fixed manifold, then all the morphisms in this category are monomorphisms, and so this will be a pole set. And in fact, it's a very specific pole set. It's just a pole set that we have been working with all the time of opens. Okay. And as I was mentioning, so now there's a final remark. So there's a big annoyance, which I have already mentioned a couple of times in my last talk, which is that disks of X is not a factorizing basis, because disks are not closed under intersections. And unlike the ordinary manifold case, I don't know of an argument in the stratified setting for how one can always assume that there's a factorizing basis of disks. And so we will basically just define this issue away. And so we will say that for now, we simply assume that X has a factorizing disk basis. So this is what we will call that. We'll say that it has enough good disks. And I think for a large class of stratified spaces, one can maybe show this, but I don't know if this is true in general. But we will just assume this and try to work like this. One can try to avoid this issue by working with hyper-co-sheaves, but I think I don't want to go into this.
Is it also called the smooth rate? Or not?
Is smooth stratified? Yes. If you drop the stratified, if you only have ordinary smooth manifolds, then this is always true. There always will exist factorizing disk spaces. But as far. Say again?
Here you work with smooth.
Smooth stratified.
Okay.
Yeah. Maybe, just the terminology maybe. So smooth stratified means it's a smooth manifold in this sense. It's not an actual manifold, it's a stratified manifold. Yeah. Okay, so now I want to talk a little bit about this condition of constructibility. So what time did I start? Does someone look at the time? Second? 35. 35, great, okay. And I will erase this. So the next thing I want to explain is, so this notion of constructibility or local constantness, which is a special case for the non-stratified case. A priori, it's not clear that this is a local condition, but this is actually true. So there's the following theorem, where I guess the original proof of this is by Ginot, and then we somehow took his proof and generalized it to the stratified setting. But the main proof idea is really Ginot. It's a very nice proof, which I will try to sketch briefly. So the statement is that I'm going to let X be a smooth stratified manifold with enough good disks. And let's say we have a factorization algebra on X, then A is constructible if and only if A is locally constructed. By locally constructible, I mean there's an open cover of X such that A restricted to each piece of the open cover is constructed. And of course, as a special case, when X is an ordinary manifold, we get the following very funny statement that says that H is locally constant if and only if A is locally constant. Yeah. Of course, you would really expect this to be true, otherwise this name would probably be a kind of a bad name, but it's not obvious at all from the definition. So let me try to sketch the Geno's proof, because it's very I find this I really like the proof. So what do we have to do? So we have to take U and V some disks of the same type. So for example, so they're both isomorphic to like this. And for simplicity, I will assume that n is equal to 0. So like there's no Rn component. This doesn't really change the argument. It just makes the picture a little bit easier to draw. So assume for simplicity. And now without loss of generality, we can assume that V is already everything. So we can assume that V is just equal to dZn, and that this is just O of X, because it's only a question about what A does in this, so the value of A on the rest of X doesn't matter. So we can just restrict to this. And so now I will draw the following picture. So this is a sort of cone. So this, since n is 0, this is just a cone on Z. So let me draw the picture where the cone, I will draw it like this, where this is the Z. I mean, technically, I would probably have to draw it dashed because it's an open cone. So this whole thing is V, and then U sits inside of it. And since it's a cone of the same type, it still needs to contain the cone point, but then it will sit inside it in a sort of squiggly way. It won't be like nicely straight embedded, as it can be very wild. But the idea is that this thing is still open. So if I go small enough, I can always find some V prime that is here, that's nicely straight and sits inside this whole V. So V prime, so this will be the cone of Z, and this will be the cone, but now of length T of Z. So this is the same as the ordinary cone, except that here you take the length to be T instead of 1. And now there's a claim that says that the map from this small cone to this big cone is an equivalence. I will explain this claim in a moment, but assuming this claim, you now see the following. You now see that, so you have V prime, V, and then here you have U, and you have the map from here to here and the map from here to here. And this composite, after you apply A, will be an equivalence. But now we can just do the same thing for U. So U is itself isomorphic to the same disk. So if we choose an isomorphism between U and the disk, which is then just a cone, then with respect to this isomorphism, we have a change of coordinates, where now in these new coordinates, our U here will be a nice straight cone, and this V prime, which was inside U, will now become like a squiggly cone. Because of course, this isomorphism need not send this nicely embedded cone to another nicely embedded cone. It will be some weird cone. But then we can just repeat the same argument. We can find a nicely embedded V prime inside here. And then by the same claim again, this will induce an equivalence. And so we see that overall, the map from V prime to A to U has both a left and a right inverse. And therefore it's an equivalence, and then since this is a retraction of it, it's also an equivalence. Let's see how much time I have. Okay. Yeah, so I think unfortunately I don't think I really have the time to go into this claim. But basically, one proves this claim by starting from here and then using the Weiss condition to like always make this cone bigger and bigger by like epsilons, and then do some transfinite composition until one arrives all the way here. But yeah, unfortunately, I think I should probably get to the rest of the lecture. I thought I would have time for this, but I don't think I will.
Where do you use the assumption that it's locally?
It's in this step. Yeah, basically in this step, you have a cone, and you're trying to extend it to an ever so slightly bigger cone, and you chose this width small enough that your algebra is locally constant on like patches from one to the next. Yeah, yeah. I can explain it. It's a very nice argument, but I think I really should get to the rest of what I have time for today. Yes. So because there is one thing I really want to talk about, which is localization. Yeah, but maybe I should probably write this. So this is here is using the local constructible. So now again, I'm going to be a little bit sketchy, but so here there's a, so Francis Tanaka, they construct an infinity category, a symmetric monoidal infinity category, which I will now call curly manifold with disjoint union. This is not the actual coproduct. Okay, it's a disjoint union of smooth manifolds. A symmetric monoidal infinity category of smooth conical manifolds. And I will just tell you some of the key features that this category has. So with such that, so here are some of the key features. So first of all, if you look at ordinary manifolds, which of course exist in here, then the space of maps from one to the other is really just the space, the usual space of embeddings, of open embeddings. And it's still sort of true if one interprets this correctly in the stratified setting, but then maybe you wouldn't know already a priori what this means. And then there's one crucial computation that they do, which says the following. If you take a fixed manifold and you look only at disks over here, I didn't say this, so disks, there's an S missing, so this is just the full subcategory of multidisks. It's the same as before, it's again a full subcategory of those things that are abstractly isomorphic to disjoint unions of conical disks. And the key computation is that if you look at the slice of disks over X, and you take the core of this, then this is equivalent to, okay, this thing of course will have many different connected components. So there will be, it will be composed over its pi 0. And let's say I have an element in its pi 0, which I will denote bracket u. Okay, then how does such a U look like? So how does an isomorphism class look like? Well, an isomorphism class will look like this, where you have a big coproduct where over some finite set, and then you have a disk of some type, and then ki many copies of that disk. So where here these ui's and uj, they're pairwise non-isomorphic. Or I. So they're pairwise non-isomorphic disks, and then each disk, of course, can appear with some multiplicity, which is this k. So this is just some natural number, I guess, bigger than 0. And this, yeah. Okay, and with this description, you can say what is the component of this space at this open, and it's just some configuration space. It's just a product over I is this I, of configuration space of ki many points in the stratum of X corresponding to ui. And I will draw a picture in a moment, so you will see what this means. So here is X ui. This is the collection of points in X with local type being this type ui. So let's draw a picture. Maybe otherwise this might be a bit hard to parse. So let's say X is, I don't know, something very explicit. Maybe there's one component like this. So it's this space. And let's say U is going to be one copy of this disk plus maybe two copies of, let's say, this. This is still a disk. And now, if you look at the corresponding configuration component of that big product, you will have a product of the configuration space. So what are the points that have this local neighborhood? Well, there's only one of them, it'll be this guy. So if this is the point little x, then you will have configurations of one point in X. Okay, this is a very big triple configuration space. And then you will have times, and now you will have a configuration of true points in the set of all those points that have a local neighborhood that looks like this. And if you write down what that is, it's going to be the points on this line, the points on this line, all the points on this line, the points on this line, plus all the points on this circle. So here is a gap. And then you will have a configuration of 2 points inside here. Okay. And the last thing we need is that, so we have an induced pointer from the straight manifold to the curly one, which of course induces a map on slices, and then even on operads. So this thing is itself again an operad, which unfortunately I don't really have time to explain how exactly one makes it into an operad, but this is again an operad. And there's one fact, that the last fact we need is that when you have an inclusion U and V in X, then U and V are abstractly isomorphic, if and only if they become this inclusion becomes an equivalence in this curly manifold. Where these are, sorry, these need to be lists. Okay, so this was maybe a lot of information dumping. I will leave it here. And then using this, we can now state we can now state, okay, I should be fine with time. So using this, we can now state the last two results for today. So the first theorem. Yeah, so this theorem has a bit of a complicated history as far as I know, because so it was originally proved by AFT, but there was a pretty significant gap in this proof, which then, from what I understand, with private communication with them, they somehow then had some argument together with Mason G. But then this never really appeared in print, and then recently we wrote a proof of this, but also Arakawa independently wrote a proof of this. And the statement is the following. So let X be a smooth conical manifold. And let's say B inside the opens of X is a multiplicative disk basis. If you want, you can just think of B as all multidisks. That's perfectly fine. That's the main use case. And then the claim is that if you take this functor from B, which sits as a sub in this open, so there will be a functor from here to curly disks over X, the claim is that this is a localization. And what is it a localization of? Well, by this last criterion, the maps here that become equivalences here are exactly at those inclusions U and V, such that U and V have the same type. And in fact, we also give an upgrade of this to a statement about operads. And very similarly, if you take the corresponding operad on the left-hand side, and here you take the corresponding operads too, this is a localization of operads. Of infinity operads. At the same maps.
This singular or?
Sorry. Okay. And so I don't think I will have time. Yeah, let me give a very, very short proof sketch, just the main input. So there's a main categorical input that one puts into this. So there's this following fact, which is a sort of recognition criterion. Which says that, oh, I think the microphone's. Thanks. Yeah. Okay, actually, I think I changed my mind. I think I will skip this for now. And if I have 2 minutes at the end, I will say it, but I think I would rather make sure I say the things I really wanted to say. which is the last ingredient one needs. So basically today, what we did is prove a bunch of statements about specifically constructible factorization algebras. And there's one more that is very relevant. So Ayala Francis Tanaka, they proved this in the locally constant case, and then we adapted the proof to the stratified setting, which says the following. It's the same setting as before. So here we still have right, we have U and V, and this is again a multiplicative disk basis, multiplicative decomposable disk basis. Again, just think about all multidisks. And then the statement is that if you have a functor from B to C, which, if you know that it's constructible, so technically I didn't say what it means for a functor to be constructible, I just said what it means for a factorization algebra to be constructible, but it's like the exact same definition, because that definition only depended on the underlying functor. And then the statement is that in this situation, if you start with something here, you don't know any Weiss condition. And yes, exactly. You don't know any Weiss condition. The only thing you know is that it's constructible. Then the statement is that if you can extend it to anything, to U, but note that, for example, U could also be B itself. The statement is that if you take A and you can extend it from here, then this is always automatically a Weiss hypercushion on U, and in particular on V. And in particular, if we care about not hypercosheaves but ordinary cosheaves, if this U is close to their intersection, which often it will be, for example, if U is everything, then this left-hand extension is also a Weiss cosheaf. Okay. So just a remark. So this argument, so I won't say anything about the proof, but just to note that this proof does use the preceding localization. So I would like to find a proof of this that doesn't use the localization, because I mean, this statement is purely in the world of the discrete operads, so you hope that maybe one can find a direct proof, but I don't know. And now we can combine these two theorems, and maybe this will be the big takeaway for the following lecture.
So should A be a factorization algebra with respect to B?
No, this is a very general statement. This is just really a statement about the underlying functors. Yeah, this is really just a statement. Of course, we're going to apply to factorization algebras in a moment, but this is really just a statement saying if you have this underlying functor which is constructible in the sense that it sends these disks. Actually, let me just quickly.
So on B, there is no assumption around Weiss anything.
No, that's the main point. Basically, what this is telling you is that the Weiss condition comes sort of for free if you're in a constructible setting. Like this should be a pretty surprising result, where like the thing I said yesterday, where if you have something Weiss and you can't extend it and it's Weiss again, that's maybe not so surprising. But this should be kind of surprising because the Weiss condition sort of comes out of nowhere, just from the constructibility. But now, let me just very quickly check to make sure. Oh, the thing is, no, yeah, no, this is the statement, yes. But so the main thing to keep in mind is the following corollary, which summarizes all of this together, which says that if X has enough good disks, of course X is still as proposed, so X is a smooth canonical manifold, then the following, so we have on the one hand factorization algebras, constructible factorization algebras on X in the sense we defined, but then you can go down to algebras which are multiplicative and constructible only on the disks of X. So this is still one categorical. You have the disks of X, but you lost the vice condition, because basically that's where this lemma comes in, that it tells you that if you're constructible, the vice condition comes automatic. And then using that localization theorem, it tells you that you can, instead of looking at the normal disks, you can look at this infinity categorical disks. And in fact, and then you can, that way you can drop the constructible, and you can even drop this n if instead of doing this to do this without the s. And this is a curly. So yeah, hopefully, so this is a, so this, just to be very clear, this is a straight D, and this is a, just so that one can see in the back, this is a curly D. Okay. So I think I'm out of time, so I will stop.
Some annoying questions. One is when you say the words localization and infinity-operads, is this synonymous with weak approximation in the sense of higher algebra?
No, it's a much more direct notion. It's just saying that. No, so okay, so if I have a map of operands and I have inside here some collection of one-area operations, then I can just say that this is a localization if for all other operads Q, the operad maps from P to Q, if this is fully faithful with the image being those things that invert W, like sort of the direct, the thing.
The thing.
Yes, exactly. But yeah, the thing we prove is like just directly this statement. Yeah. Mm-hmm.
So if you think X to just be Rn without stratification, is this this over Rn is literally the n of R?
Let's think. It's not like lich. I don't know. It depends on how literal is.
So, then that.
If you have, I guess if you take single disks. Yeah, I think so, because if X is Rn and you have here just this, which then will just be Rn itself, and this slice will just have a single object, which will just be some inclusion from Rn itself, and then the operatic structure, and this should exactly give you the AN operatic structure. Yeah.
You recover the locally constant factorization algebras.
Yes, that's right.
A corollary question to this: if X is just a different smooth manifold, which is not stratified, is this E of the fundamental?
So I'm not 100% sure about this. I think there might be some subtlety, which I'm not. So I have to say I've never like fully understood that definition. So I don't think I want to commit to answer this question.